Greetings, dear student. In last session, we reviewed the stepwise procedure for solving a numerical based on slope deflection method. Today, we'll solve a numerical on SDM. Numerical statement is analyze the beam shown in figure using SDM, means slope deflection method. Also draw SFD and BMD. SFD is here stand for shear force diagram and bending moment diagram. The given beam is a two-span continuous beam where A and C support are fixed support and B is the intermediate support. AB span is of 4 meter with moment of inertia I and BC span is of 3 meter with moment of inertia I. Within the span A to B, a point load acts at a mid span, whereas for the span BC, there is an UDL of 10 kN per meter. Now to start with, the very first step is to find out degree of kinematic indeterminacy. Degree of kinematic indeterminacy is nothing but the available degrees of freedom within the structure. For this, we need to identify the unknown displacement in the structure. The given structure is a beam subjected to a gravity loads. The predominant action will be the bending here. Due to bending, there will be development of rotation at the ends and deflection at the ends. So, the unknown displacement will be here, rotation and displacement at the joint. Let us consider ABC joint. At joint A, we can have theta A rotation, B theta B rotation, C theta C rotation. If we talk about the displacement may be delta A, delta B and delta C. Now, with reference to a given condition and A is fixed means there will be no rotation at the end A and there will be no displacement at the end A as since no sinking has been mentioned at joint A. Similar way, the joint B is a joint B is continuous for both the span or common joint for both the span AB and BC. It will have a rotation, but sinking is not given. That's why we will not consider any sinking at the joint B. That's why unknown displacement will not be considered here. Now joint C is fixed. That's why there will be no development of rotation at the end C, as well as settlement is not given. That's why we will not consider the degrees of freedom at this particular joint. That's why the only available degree of freedom with us is theta B. It means that the degree of kinematic indeterminacy of our structure is 1. We need to write one additional equation in terms of compatibility to get the unknown forces in the member. Let's move towards the step number 2. Step number 2 is finding out the fixed end moments. For finding fixed end moments, we'll assume all joints are locked and we'll divide this beam into two equal parts. Let us say it is A to B and B to C. If we see A to B, it is a standard case of fixed beam subjected to a point load at mid span. So we can find the moment at the ends, MFAB equals to minus WL by 8. If you substitute the values here, 50 into 4 divided by 8, you'll get the magnitude as a minus 25 kilonewton meter. Similar, the end B, MFBA is equals to plus WL by 8. If you substitute the values of load here, 50 into 4 divided by 8, it results to 25 kilonewton meter. The second case is a beam subjected to a UDL, fixed beam subjected to a UDL. In this case, we can get the moment at the ends by the relation MFBC equals to minus WL square by 12 minus 10 into 3 square divided by 12 result to minus 7.5 kilonewton meter moment. Now at the end C, we are going to get a moment by the relation plus WL square by 12, which results into a value of plus 7.5 kilonewton meter. Now step 3, we have to write slope deflection relationship at each joint. Let us write a relationship for the joint A. So I am writing here MAB, means I am at a joint A and moving towards in the path B. So it will be equals to MFAB plus 4 EI theta A divided by L plus 2 EI theta B by L plus minus 6 EI delta by L square. The first component is the fixed end moments. The second two components are the effects of rotation. One is at the near end and one is at the far end. Whereas 6 EI, the third component is nothing but the effect due to displacement. Now, if I talk about the arrangement of the equation, if I say M A to B, the first part I have written about A. So, the moment MF will be A to B. Then 4 EI will be assigned with reference to first alphabet which is getting here theta A. Then half the partial transfer will be with reference to the second alphabet which is coming here B. This is what I am saying for a thumb rule to be remembered for remembering the formula to apply at a particular joint. If I apply this one, so what I'm going to get from the end condition, theta A is a fix. That's why this rotational component will not be considered. It will become 0. And since the displacement is not given, sinking is not given at the joint, that's why the effect of sinking displacement will also neglected. So we will left with the relation minus 25 plus 2 EI theta B by 4. After substituting these values, respective values of span and loads, we are getting this relation. Further, if we solve it or simplify it, we'll get the relation MAB equals to minus 25 plus 0.5 EI theta B. Now we'll apply the equation for the joint B. Here, if I am starting for the joint B, B to A, I will look up the moment, fixed moment from B to A. Then 4 EI theta B by L. Now here 4 EI is associated with the B here, whereas 2 EI means half the partial transfer will be there 2 EI theta A with reference to A joint plus 6 EI delta by L square. Since sinking and rotation at the end A is not given to us, that's why the relation left with us is equals to 25 plus 4 EI theta B by 4. So after solving this further, we get MBA equals to 25 plus EI theta B. Let this be equation number 2. Now if I apply the slope deflection relation at joint C, I am getting a relation MBC equals to MFBC plus 4 EI theta B by L plus 2 EI theta C by L plus minus 6 EI delta by L square. Since and C is been fixed, locked, that's why rotational contribution will not be considered and displacement is not given. That's why displacement component will not be considered here. The leftover relation is minus 7.5 plus 4 EI theta B by 3. If I substitute or simplify this further, I will get a relation MBC equals to minus 7.5 plus 1.33 EI theta B. Now I will apply for the joint C. So here MFC to be the fixed moment will be counted plus 4 EI theta C by L plus 2 EI theta B by L plus minus 6 EI delta by L. As joint C is locked, the contribution for this rotational and displacement component will be not utilized. That's why the relation left with us is CB is equals to 7.5 plus 2 EI theta B by 3. If I simplify further, I will get MCB equals to 7.5 plus 0.67 EI theta B. This is the slope deflection relation which we have reached at each joint. Next step is to calibrate equilibrium equation at the joint B. Okay, for this we'll have the equilibrium of the span moments. If I talk about the joint B, I'm getting a span moments which are encircled in a dotted lines here. So I will take a balance of these two. Means MFBA plus MFBC should be equals to 0. This will be the equilibrium condition at this particular joint. So if we further solve this by substituting the relationship which we have in earlier case, so 25 plus EI theta B minus 7.5 plus 1.33 EI theta B means equation 2 and equation 3 has been added to get the answer for this particular equilibrium equation. So from this we get unknown theta B as a minus 7.51 upon EI. Once we got the unknown, we'll back substitute this into the uh, your slope deflection equation relationship to get a final moments. The first relation we have MA to B equals to minus 25 plus 0.5 EI theta B. If I substitute the value of EI theta B here, minus 7.51 upon EI get cancelled. What remains is minus 28.75 kilonewton meter. Similar way, I will write for B to A 25 plus EI theta B. Substitute the values of EI theta B, will get the value 17.50 for MBA. Similarly, for BC, we will write this and we'll get a relation minus 17.50 kilonewton meter. And for C to B, I am going to get the value as a 2.46 kilonewton meter. Likewise, we'll get the final moments at each end. Once we got the final moment at each end, we are able to find out the unknown reactive forces and their distribution over the span. Let's begin with the span A to B. In the span A to B, we will have the two end moments. One is MB to A, which we have evaluated as 28.75. Then 17.50, this is MB2. B to A to B and B to A, we have substituted here. Now applied loading condition is 50 kilonewton at the mid span. The reactive forces generated at the end A in vertical direction is RA, and here I will write it as a second part RB1. Why RB1? Because it is being common joint between the two span. That's why it will have both the side contribution. The first contribution I'm going to consider from A to B. That's why RB1. If I write equilibrium equation in vertical direction for this particular case, we get a relation Ra plus Rb1 equals to 50. And if I take summation of moment about the joint A, the moment at the joint A will be a resultant of the effects due to reactive force and all forces acting on this along the span. So we can write it as a minus 4 Rb1, minus 4 because it is going to have anti-clockwise rotation. RB will give me anti-clockwise rotation about the joint A. Minus 28.75, this is the contribution of your moment at the end A. Plus 50 into 2, this is the moment caused by the applied force at mid-span. Plus 17.50, it is a moment at the end B. From this we get RB1 value as a 22.18. Once we get RB1, we'll back substitute this into the earlier relationship. From that we can get Ra equals to 50 minus Rb1, which result into a value of 27.82. Now we'll go for the second span. In second span, we will have the reactive forces at the end B as a Rb2 and end C as a Rc. Rb2 is this is a B joint which is common between the span. That's why second part I'm going to consider here. Moments I have mentioned here, which we have evaluated from the earlier statics. So if I take summation of forces along vertical direction, I get a relation Rb2 plus Rc equals to 30. If I take moment about the joint B, I should write here joint B. So I will get an effect, anti-clockwise effect of Rc minus 3 Rc minus 17.50 plus 10 into 3 into 3 by 2, the couple produced by the UDL, plus 2.46 the moment at the joint C. From this, Rc value comes out to be 9.98. Now I will write Rb2 equals to 30 minus Ra. That's why Rb2 value work out to be 20.02. Now if I add both the component at the joint B, Rb1 from the first span, Rb2 from the second span, the total value of reactive force Rb comes to be 42.20. Now once we got the reactive forces and moment along the joints, so we can have the construction of variation of shear force along the span. So the shear force diagram work out to be like this. At A, we will have 27.82. Below the load, there is a variation from 28.782 to 21.18. Then at B, we will going to get the variation like this, and at the C, this will be the shear force diagram for the available forces at the respective joints. Similarly, we can draw the bending moment diagram, which shows the distribution of the moments which we have received after the solution of slope deflection equations. So this is a fixed end moment at the this is a moment final moment at the end A. This one is the moment at the end B, and this one is the moment at the C. If I want to get a net effect here, I have to overlap this with a free moment diagram, which we can obtain for the individual span based on the loading condition. For the first case, we have the span as a simply supported with a point load at midpoint. For that, we have relation WL by 4. If I substitute here the values of respective load here, 50 into 4 divided by 4, the answer comes to 50 kilonewton meter. Similarly, in the second case, it will be simply supported being subjected to UDL of magnitude 10. For that, we have relation WL square by 8. If I do the statics, I will get the value as 11.25. If I overlap these two, I will get the area which is being under a common integration. The area under common integration, if I consider, this will be said to be a net bending moment diagram for the given case. That's all. We have solved the shear force. We have drawn the shear force diagram. We have drawn the BMD diagram, and total analysis of the numerical has been completed. We'll come with much more articles, much more numericals in forthcoming lecture. Till then, goodbye. Thank you.